In the quiet hum of a computer lab, in the soft whir of machinery, there exists a story of something so simple, so elegant, that it changed everything. Tonight, we're going to explore the silent logic of the floppy disk.
Take a slow breath. Settle in. Because this is a journey through engineering history, through human ingenuity, through the small moments that transformed how we work with information. Let's begin at the beginning. What is a floppy disk? At its most fundamental level, a floppy disk is a removable magnetic storage disk. It was designed to store and transfer computer data, read and written by a device called a floppy disk drive. That's the simple answer, the technical answer. But that definition doesn't capture what it truly was. A floppy disk was a revolution. It was freedom. It was the ability to carry your work, your programs, your data in your hand, to move it from one machine to another, to share it, to preserve it. Picture this small, flexible disk, protected by a square plastic jacket, no bigger than your hand. Inside that simple package was the power to hold thousands of pages of text, entire programs, databases, the work of weeks or months, all contained in something you could slip into an envelope and mail across the country. For nearly 3 decades, from the 1970s through the 1990s, floppy disks were the primary way people distributed software. They were how you moved files between computers, how you made backups of important work. They sat in drawers and boxes in offices and homes around the world, each one a small library of magnetic memory. But to understand why the floppy disk mattered so much, we need to travel back further. We need to understand the world that existed before it. Imagine yourself in the 1960s. You're working with computers, but these aren't the computers you know today. These are massive machines, mainframes. They fill entire rooms. They hum with the sound of spinning tape drives and clicking relays. And to feed them information, to give them their instructions, you use punched cards. Punched cards, thin rectangles of stiff paper, each one about the size of a dollar bill. Each card could hold a single line of code or a single record of data. Holes punched in specific positions represented information, a kind of physical binary code you could see and touch. This was how computing worked. Programmers would write their code by hand, then take their handwritten sheets to key punch operators, who would sit at special machines and punch out card after card after card. 1 line of code, 1 card. 100 lines of code, 100 cards. These cards would be carefully gathered into decks, held together with rubber bands, placed in boxes. A single program might require hundreds or thousands of cards, and these decks had to be kept in perfect order. Because the sequence mattered, card 1 had to come before card 2 had to come before card 3. Think about what this meant in practice. You're a programmer with a deck of 500 cards. You need to take it to the computer room. You're walking down a hallway, and you trip. The rubber band breaks. 500 cards scatter across the floor. Each one looks nearly identical to every other, but they have to go back in exactly the right order, or your program won't work. Or perhaps you don't drop them. You make it to the computer room safely. You feed your deck into the card reader. The machine begins processing your program. And then, error. Something's wrong. You need to fix 1 line of code. That means finding the right card in your deck, punching a new card, removing the old one, inserting the new one in exactly the right position. Computer centers had special rules. No running in the halls. No sudden movements near card decks. Some programmers would number their cards by hand in the margins, just in case. Others would draw a diagonal line across the top edge of an entire deck, so that if the cards got mixed up, you could use the line to help sort them back into order. This was the reality of computing in the 1960s. And it wasn't just inconvenient, it was becoming impossible. Because the world was changing. Organizations were moving toward automated computing. Businesses needed to process more data. Scientists needed to run larger simulations. The military needed more powerful calculations. And punch cards, for all their decades of faithful service, were becoming a bottleneck. They were bulky. A single program might fill multiple boxes. Moving them around required physical space and physical labor. They were heavy. If you needed to transport a large application, you might need a cart. They were inefficient. Every time you needed to update software, you needed to distribute new decks of cards. Installing a program meant feeding thousands of cards through a reader, one at a time. The mechanical readers were loud and slow. They could jam. They could damage cards. And punch cards were fragile. Not in an obvious way, not like glass or paper, but fragile in their own peculiar way. A bent corner could cause a misread. A torn edge could jam a reader. Coffee spilled on a deck could destroy hours of work. And they were vulnerable to simple human error. One misplaced card, one card in the wrong order, and nothing worked. As organizations expanded their use of computers, as automation became more critical, these limitations became more painful. Every programming job involved handling these physical artifacts. Every software update required physical distribution. Every backup required duplicate decks of cards. The punch card had served computing well since the late 1800s. Herman Hollerith had used them to tabulate the 1890 U.S. Census. IBM had built its business around them. They were familiar, standardized, reliable in their own way. But they represented an older philosophy of computing. They were rooted in an era when computers were rare and precious, when computing time was scheduled in advance, when programs were carefully prepared and checked before being submitted to the machine. The world was ready for something new, something that could hold more information in less space, something more durable, something faster to work with, something that could bridge the gap between the familiar world of IBM's punched card infrastructure and the future that everyone could see coming. Engineers at IBM understood this. They could see the limitations. They could see the frustration. They could see organizations struggling to scale their computing operations while still dependent on these rectangular pieces of cardboard. And so they began working on something different, something that would change everything. But we're getting ahead of ourselves. Let's pause here for a moment. Let's sit with the image of those card decks. The careful handling, the rubber bands, the numbered sequences, the fear of that accidental spill or drop. Because in that world of fragility and bulk and careful ordering, in that world of physical data you could hold and see and accidentally destroy, the need for something better was becoming undeniable. The stage was set. The problem was clear. And at IBM, in the late 1960s, engineers were about to create the solution. Yes, I apologize for the delay. Let me continue writing all the remaining segments for you right now. In the laboratories of IBM, in the late 1960s, a team of engineers gathered around a problem. They knew what they needed to create. Something smaller than card decks, something more reliable, something that could store far more information, and do it all in a form that would still fit into the workflows IBM's customers already knew. This wasn't just an engineering challenge. It was a question of evolution. How do you move an entire industry forward without breaking everything that already exists? The answer would come from a team led by a man named Alan Shugart, an engineer with vision, someone who understood both the technical possibilities and the practical realities of how businesses actually worked. Alan Shugart and his team at IBM didn't just wake up one morning with the idea fully formed. No great invention works that way. Instead, they began with the constraints, the requirements, the problems they needed to solve. IBM's mainframe computers needed a way to load microcode, the fundamental instructions that told the computer how to be a computer. They needed to load software, programs, and operating systems, and they needed something that could be used in the field, by technicians, by operators, by people who weren't necessarily computer scientists. The team began their work somewhere around 1967. They experimented, they tested, they tried different approaches. Magnetic tape existed, but it was sequential. You had to wind through it to find what you needed. Punched cards were random access. You could pull out any card, but they were bulky and fragile. What if? What if you could combine the best of both worlds? What if you could create something with the capacity of magnetic tape, but the removability and accessibility of punched cards? They worked with flexible magnetic media, thin sheets of plastic, coated with iron oxide, the same basic technology that was used in tape recorders and magnetic tape, but formed into a disc instead of a ribbon. The disc would spin. A read/write head would move across its surface. And because it was a disc, because it spun in place, you could move that head directly to any position. Random access, like cards, but magnetic, like tape. They enclosed the disc in a protective jacket, square, sturdy, with openings that allowed the head to touch the media, but which protected the rest of the disc from fingerprints and dust. 1. By 1971, they had it. The first commercial floppy disk, 8 inches across, larger than anything that would come later, but revolutionary nonetheless. These early disks were designed for business systems, for mainframes, for the serious computing that IBM's customers relied upon. They weren't toys, they weren't consumer products, they were professional tools for professional environments. And they worked. Oh, how they worked. Think about what this meant. Take a moment to really consider it. One of these original 8-inch floppy disks, just one, could hold the equivalent of about 3,000 punch cards. 3,000 cards. Imagine a programmer standing in an IBM computer center in 1971. In one hand, a single floppy disk, thin, light, flexible. In the other hand, imagine them gesturing to a stack of card decks. Boxes full of them. Heavy, bulky, requiring careful organization. All of that, reduced to this one disk. Instead of feeding long stacks of cards through a reader, watching them click by one at a time, waiting for jams, listening to that mechanical chatter, an operator could simply insert a single disk, slide it into a drive, close the latch, and the computer could read all that information. Faster, more reliably, with far less mechanical complexity. The capacity difference was profound, but capacity alone wasn't the only advantage. Let's count the ways the floppy disk improved upon what came before. Space. A floppy disk took up far less physical space than equivalent card decks. You could store dozens of disks in the space that used to hold one large program on cards. File cabinets that once groaned with the weight of cardboard could now hold entire libraries of software on disks. Weight. If you needed to transport programs or data, you no longer needed a cart. You could carry disks in your briefcase, mail them in padded envelopes. The physical burden of data literally lightened the protective jacket. This was simple but crucial. The disk itself was flexible, hence the name floppy, but it lived inside a square protective jacket. That jacket had a fabric lining that cleaned the disk surface as it spun. It had cutouts for the drive's head to access the media, but the rest of the disk stayed protected from fingerprints, from dust, from the casual damage that could destroy a punched card. Handling became easier. No more careful ordering of hundreds of sequential items. No more fear of dropping a deck and spending hours trying to reconstruct the sequence. A disk was a single unit, atomic, complete. Reliability improved. Mechanical card readers had moving parts that grabbed and pulled each card through. They could jam. Cards could tear. With a floppy disk, the mechanics were simpler. The disk spun in place. The head moved on a track. Fewer points of failure. Smoother operation. And perhaps most importantly, error rates decreased. Random human errors, a card in the wrong place, a card accidentally duplicated or skipped. These became impossible. The data on the disk was stored magnetically, sequentially within tracks and sectors. The drive read it in the correct order automatically, every time. For IBM's customers, this meant something profound. It meant they could move faster, deploy software more quickly, update systems with less effort, maintain backups more easily. Everything about working with computer data became more efficient. But there was another advantage that Alan Shugart and his team had built in. Something subtle, something that showed real understanding of how businesses actually operated. The floppy disk fit into IBM's existing world. It didn't require throwing everything out and starting over. Computer centers already had processes for managing media. They had storage systems, cataloging methods, security procedures. The floppy disk was different enough to solve problems, but similar enough to feel familiar. It was a bridge technology. That's the perfect term for it. A bridge. It connected the known world of physical media and established workflows to the future world of magnetic storage and higher capacity. And this wasn't an accident. Engineers don't just build things that work technically. The best engineers build things that work in the real world, in organizations, with people, with existing infrastructure and established habits. The 8-inch floppy succeeded because it was both revolutionary and practical. It changed everything while asking users to change as little as possible. In those early days of the 1970s, as these disks began appearing in computer centers, as operators first slid them into drives and watched them work, something shifted, not dramatically, not overnight, but steadily, inevitably. The mountain of cardboard began to shrink. The boxes of punched cards, slowly, started to disappear. Filing cabinets were reorganized. Workflows were updated. And all across IBM's customer base, from insurance companies to government agencies to research laboratories, computing became a little bit faster, a little bit easier, a little bit more reliable. This was the gift that Alan Shugart and his team gave to the world. Not just a technology, but a transformation, a way forward, a solution to a problem that everyone had been living with. So long they'd almost forgotten it was a problem. The floppy disk was born, and the world of computing would never be the same. But we're still in the early days of this story. The 8-inch disk was just the beginning. Engineers would refine it, shrink it, improve it, push the boundaries of what magnetic storage could do, and through all of that evolution, through all those improvements, the fundamental elegance of the idea would remain. A spinning disk, a moving head, magnetic media, all protected in a simple jacket, silent logic, simple physics, engineering history, happening one disk at a time. Now we arrive at something beautiful, something elegant in its complexity. The question that sits at the heart of magnetic storage: how does a floppy disk actually remember? Take a breath, slow down, because we're about to explore something that happens at scales too small to see, at speeds too fast to follow, but with a logic so clear, so pure, that once you understand it, you'll never look at magnetic storage the same way again. Data on a floppy disk is stored in concentric tracks. Imagine looking down at the disk from above. Picture circles within circles within circles, like the rings of a tree, but perfectly round, perfectly spaced, each one independent of the others. These tracks are divided into sectors, pie slices, sections. Each sector holds a specific amount of data. The disk spins, the head moves, and together, these two motions, circular and linear, create a coordinate system, a way to find any piece of information. Track 5, Sector 3. Track 12, Sector 8. But how does the disk actually hold information? How do you store a 0 or a 1, a bit of data, on a physical surface? The answer is magnetism, that fundamental force, the same force that makes compass needles point north, the same force that lets refrigerator magnets cling to metal, that ancient, invisible force that humans have known about for thousands of years, put to work storing the digital thoughts of computers. The floppy disk surface is coated with a thin layer of magnetic material, iron oxide typically, rust essentially, but very carefully prepared rust. Particles of it suspended in a binder and spread evenly across the plastic substrate. Each tiny region of this coating can be magnetized. And here's the crucial part. It can be magnetized in one direction or the other, north-south or south-north, positive or negative, 1 or 0. When you want to write data to the disk, when you want to store a bit of information, an electrical current passes through a coil in the right head. This current creates a magnetic field. That field reaches down through the tiny gap between the head and the disk surface and magnetizes a small region of the coating. The direction of the current determines the direction of magnetization. Current flowing one way creates north-pointing magnetization. Current flowing the other way creates south-pointing magnetization. Binary, digital, on or off, 1 or 0. And here's what makes magnetic storage so remarkable. Once you've magnetized those particles, once you've set their direction, they stay that way. They remember, even when you remove the disk from the drive, even when you turn off the computer, even years later, those magnetic particles remain aligned in the pattern you set. This is persistent memory. Memory that doesn't need power. Memory that waits patiently, silently, for someone to come along and read it. And reading is just as elegant as writing. When you want to read data back, when you want to retrieve those stored bits, the read head passes over the disk surface. As it moves across regions of different magnetization, the changing magnetic field induces tiny electrical currents in the head's coil. These currents are incredibly small, whispers of electricity, but they're there, and they follow a pattern. As the head crosses from a region magnetized one way to a region magnetized the other way, a pulse of current flows. That pulse can be detected, amplified, decoded. The electronics in the drive are listening for these pulses, counting them, timing them, interpreting them, converting those tiny magnetic whispers back into the ones and zeros that computers understand. But now we come to one of the most fascinating aspects of floppy disk engineering, something that seems almost impossible when you first learn about it. The read/write head, that small metal component that does all this magnetic reading and writing, doesn't actually touch the disk surface. It flies. Not in the way a plane flies, not with lift and thrust, but in its own peculiar way, on a cushion of air so thin you couldn't slip a hair into it. A microscopic gap maintained by one of the most elegant tricks in mechanical engineering. Here's how it works. The disk spins. As it spins, it drags air along with it. The surface of the spinning disk is moving, and the air molecules right at that surface are moving too. Friction, viscosity, the same force that makes it hard to stir honey. The read/write head is shaped carefully, designed with aerodynamics in mind. As the moving air encounters the head, it creates pressure. That pressure pushes the head away from the disk surface, just barely, just enough. The head literally rides on an air bearing, a layer of air molecules trapped between the head and the disk, pushed there by the motion of the disk itself, maintained by the constant spinning, present only when the disk is moving. This is crucial, absolutely crucial, because if the head scraped directly against the disk surface, friction would generate heat, wear, damage. The magnetic coating would degrade, the head would wear down, the disk would fail. But with this air bearing, with this microscopic cushion, the head hovers, always close, close enough that the magnetic fields can reach across that gap, close enough to read the tiniest variations in magnetization, but never touching, never wearing, never scraping. This gap is measured in microinches, millionths of an inch, smaller than a particle of cigarette smoke, smaller than a human hair by several orders of magnitude. The precision required to maintain this gap, to design heads that fly at exactly the right height, is extraordinary. Think about what this means. Every time you inserted a floppy disk into a drive, every time you heard that soft whir as the motor spun up, this delicate dance was beginning. The disk would start spinning. Air would start moving. The head would lift, just barely, settling into its flying height. And then the reading and writing could begin. The head would step from track to track, moving in discrete jumps on its mechanical arm. The disk would continue spinning at constant speed, and data would flow. When writing, electrical currents pulsing through the head coil, magnetic fields reaching across that air gap, particles of iron oxide responding, aligning, remembering. When reading, the head sweeping over previously magnetized regions, magnetic fields changing, tiny currents induced, signals detected and decoded. All of this happening at speeds that made it seem instant to human perception. You'd press save. A light would blink. A moment later, done. Your data was stored, your work was preserved. But in that moment, at the scale of the disk itself, entire dramas were playing out. Thousands of magnetic transitions being written, electrical currents flowing in precise patterns, the head flying on its air cushion, tracking perfectly, maintaining its position through mechanical precision and aerodynamic forces. The position of the head was controlled mechanically. A stepper motor or a voice coil actuator would move the head arm, one track at a time, or sweeping across multiple tracks to reach the desired position. Physical motion, precise and repeatable, but the spacing, that critical flying height, was maintained purely by the physics of moving air. No active control, no feedback system, just careful design. The right shape, the right speed, the right balance of forces. This was engineering at its finest, taking multiple challenges, magnetic storage, mechanical positioning, aerodynamic spacing, and solving them all together in one elegant system. And the remarkable thing is that this worked. Reliably. Millions of floppy drives built over decades. Billions of disks manufactured and used and reused. And this flying head system, this air bearing that seemed so delicate, worked day after day, year after year. Of course, it wasn't perfect. Nothing is. Dust was the enemy. A particle of dust on the disk surface was like a boulder to the flying head. If the disk surface was contaminated, if someone touched the magnetic media with a fingerprint, If dust got inside the protective jacket, the head might encounter something. Contact might occur. This is why the protective jacket was so important. Why there were warnings on every disc. Do not touch the magnetic surface. Why the jacket had a fabric lining that gently cleaned the disc as it spun. Every precaution was necessary because that air-bearing gap was so small, so unforgiving. When reading, when decoding those magnetic transitions, the electronics were looking for changes, not absolute values, not this region is magnetized north, but rather, here's where the magnetization changes from north to south. These transitions were what mattered. These were what encoded the data. The timing between transitions carried information. The pattern of changes. Sophisticated encoding schemes were developed to pack more data into those magnetic patterns, to make the storage more efficient, more reliable, more forgiving of imperfections. But underneath all those encoding schemes, underneath the error correction and the file systems and the formatting, the fundamental principle remained constant. Magnetic particles, aligned by electrical currents, rid by induced signals. Persistent, patient, waiting to give up their secrets when asked. This is what happened every time you saved a file, every time you loaded a program, every time you heard that soft mechanical sound of a drive seeking, stepping from track to track, finding the right sector, positioning the head, silent logic, invisible forces, magnetic memory written at microscopic scales. And it all worked, reliably enough, well enough, to change the world. Let that sink in for a moment. This technology that seems almost magical when you understand how small the scales are, how precise the tolerances must be, how delicate the balance of forces. This was mass-produced, made affordable, put into millions of computers, used by people who never knew or needed to know how it actually worked. They just knew it did. Insert disk, save file, remove disk, take it to another computer. Insert, load file. The data was there, preserved, transported, reliable. Engineering magic, made mundane through production, made ordinary through reliability. The best kind of magic, the kind that works. The story of the floppy disk is not a single story. It's a story of evolution, of refinement, of engineers asking, again and again, can we make this smaller? Can we make it hold more? Can we make it better? Over the course of about 3 decades, from the early 1970s to the early 2000s, the floppy disk transformed, not once, not twice, but in waves, each generation learning from the last, each iteration pushing a little further. 3 main sizes emerged, 3 formats that would define different eras, different needs, different visions of what portable storage should be. 8 inches, 5¼ inches, 3½ inches. Each one has its own story, its own moment, its own reason for being. Let's start where we began, with that original 8-inch format, the one that IBM introduced around 1971, the grandfather of them all. 8 inches across, large by modern standards, large even by the standards of what would come just a few years later. But remember the context. Remember what it was replacing. Compared to decks of punched cards, compared to boxes full of cardboard, 8 inches was compact, revolutionary. Those early 8-inch disks stored roughly 80 kilobytes, 80,000 bytes, 80,000 characters, enough for perhaps 40 pages of text. It doesn't sound like much now, but in 1971, compared to 3,000 punched cards, it was liberation. The 8-inch format continued to evolve throughout the 1970s. Engineers found ways to pack more data onto the same physical surface, better magnetic coatings, tighter track spacing, more sophisticated encoding methods. By the late 1970s, early 1980s, 8-inch discs could hold about 1.2 megabytes, 15 times the capacity of those first discs. But even as the 8-inch format was maturing, even as it was becoming the standard for business computing and mainframe work, engineers were already thinking smaller. Why? Because computers themselves were changing. The late 1970s saw the birth of personal computers. Not massive mainframes locked in climate-controlled rooms, but smaller machines. Machines you could fit on a desk. Machines designed for individuals rather than entire organizations. These new computers needed storage, but they didn't need 8-inch drives. Those drives were too large, too expensive, too much for a personal machine. And so, around 1976, the 5¼ floppy disk was born. 5¼ inches, still larger than your hand, still requiring a drive mechanism, but meaningfully smaller than what came before. Small enough to fit in the emerging personal computers, affordable enough for individual users. The early 5¼ inch disks were modest. They stored about 90 to 160 kilobytes, less than those advanced 8-inch disks. But that was fine. They served a different market, a different need. Personal computing wasn't about mainframe-scale data processing. It was about word processing, simple databases, educational software, games, and the 5¼ inch format had advantages beyond just size. The disks were cheaper to manufacture. The drives were simpler, less expensive, more suitable for mass production, for a market that was about to explode. Through the late 1970s and into the 1980s, as personal computers spread from hobbyists to businesses to homes, the 5¼ inch discs spread with them. Apple II computers used them. The IBM PC, when it launched in 1981, used them. Commodore, Atari, Tandy. Every major personal computer manufacturer adopted the format. And like the 8-inch format before it, the 5¼ inch disc evolved. Early discs were single-sided. You could only store data on one surface. Then double-sided discs appeared. You could flip them over, or more commonly, drives were built with heads on both sides, doubling the capacity. Density increased. Those early 90 kilobyte disks gave way to 360 kilobyte disks. Then higher density versions storing 1.2 megabytes. The same physical size, the same basic mechanism, but more and more data packed into the same space. You could watch this evolution in real time if you were using computers in the early 1980s. You'd buy a box of disks, single-sided, single density. A few months later, the store would have double-sided disks, same price, twice the storage. A year later, high-density disks, 4 times the original capacity, same physical format, same size drive, just better. But the 5¼ inch disc had a problem that would ultimately doom it. It was flexible. Too flexible. The disc itself, the actual magnetic media, was thin plastic, bendable, and while it lived in a protective jacket, that jacket was also somewhat flexible. You could bend a 5¼ inch disc, not dramatically, but enough to potentially damage it, enough that you had to be careful. The disc could be creased, warped. The magnetic surface could be scratched if the jacket was damaged. And there was another issue. The center hole, the spindle opening, on a 5¼ inch disc. This was just a hole, no reinforcement. The drive spindle would clamp onto this area, and over time, with repeated use, the disc could become damaged right at that critical point where the drive gripped it. Engineers looked at these limitations. They looked at the increasing importance of data, the increasing need for reliability, for durability, for storage that could be handled more casually, carried in a pocket, tossed in a bag without worry. And in the early 1980s, they created something new, something that would become the iconic image of the floppy disk, the format that would appear in the save icon that persists to this day. The 3.5-inch floppy disk, 3.5 inches, smaller than the 5.25, small enough to truly be portable, to slip into a shirt pocket, to mail in a standard envelope. But the size was just the beginning. The real innovation was in the construction. The 3.5-inch disk used a rigid plastic shell, not cardboard, not flexible material, hard plastic, durable, protective. That rigid shell made all the difference. You could drop a 3.5-inch disk. Not that you should, but you could, and it would probably be fine. The rigid shell protected the magnetic media inside, kept it flat, kept it clean. The center hub was reinforced with metal, a small metal ring that the drive spindle engaged with. This prevented wear, prevented deformation, made the disk last longer through more read-write cycles. And there was a metal shutter, a sliding cover over the opening where the drive's head accessed the media. When the disk was outside a drive, the shutter was closed, protecting the magnetic surface from dust, from fingerprints, from contamination. When you inserted the disk into a drive, the drive's mechanism would slide the shutter open, access the media. Then when you ejected the disk, the shutter would snap closed again. This attention to physical durability, to protection, to practical handling, made the 3.5-inch disk more reliable, more user-friendly, better suited to an era when more and more people were using computers, people who weren't engineers, who weren't experts, who just wanted their data to be safe. The 3.5-inch format was standardized in the early 1980s. Early versions stored 360 to 720 kilobytes. But the most common version, the one that would become ubiquitous, was the high-density format, 1.44 megabytes. That was the magic number, the standard capacity that everyone came to know. 1.44 megabytes. Enough for a substantial document, a small program, a collection of files, not enormous by later standards, but for its time, for its size, impressive. Inside that 1.44 megabytes was room for about 1,400 pages of plain text, or a small database, or system files, or a game, or thousands of emails, or a photo, if you compressed it enough. The 3.25-inch disk had one more trick, one more capacity option, a 2.88 megabyte extended density format, twice the storage of the standard high-density disk. This existed. It was real. Drives were manufactured. But it never caught on, never achieved widespread adoption. By the time 2.88 megabyte drives were available, other technologies were already emerging. The extra capacity wasn't enough to justify the cost. The incompatibility with standard drives was a barrier. And so this format remains a footnote, a path not taken. But the 1.44 megabyte format, that became everything. Through the late 1980s, through the entire 1990s, into the early 2000s. The 3.5-inch high-density floppy disk was the standard. Almost every computer sold had a floppy drive. Almost every software package could fit on one or a few floppy disks. Almost everyone who used a computer knew the ritual. Insert disk. Wait for the light. The soft sound of the drive engaging. The spinning. The seeking. The data transferring. 3 formats. 3 eras. 8 inches for the mainframe age. 5.25 inches for the personal computer revolution. 3.5 inches for the age of mass computing. Each one building on what came before. Each one solving new problems. Each one optimized for its moment, its market, its needs. The progression wasn't just about getting smaller. It was about getting better, more reliable, more durable, more suited to how people actually use computers, how they actually handle data. From those first 80 kilobyte 8-inch disks to the 1.44 megabyte 3.5-inch standard, capacity increased 18-fold, but the physical volume decreased dramatically. The reliability improved, the ease of use improved, the cost per megabyte fell. This is what good engineering looks like. Not just making something work, but making it better. Generation after generation, iteration after iteration, learning, refining, responding to real-world use and real-world needs. And through all these changes, through all these different sizes and capacities, the fundamental principle remained the same. A spinning disk, magnetic storage, a read-write head, tracks and sectors, the silent logic of magnetism, translated into ones and zeros, preserved in iron oxide, waiting to be read. 30 years of evolution, 3 major formats, countless millions of disks manufactured, billions of files stored. The floppy disk in all its forms became part of the fabric of computing, part of how people worked, how they shared information, how they backed up their precious data. And even now, long after the floppy disk has faded from daily use, that 3.5-inch form persists in the save icon, in our collective memory, a symbol of an era, a reminder of how far we've come, but also a reminder of elegant engineering, of iterative improvement, of technology that served its purpose, faithfully, for decades. There's something satisfying about efficiency, about finding ways to pack more into less, about squeezing every last bit of capacity from a given space. Engineers understand this satisfaction deeply. It's not just about numbers, it's about elegance, about optimization, about making things better without making them bigger. The evolution of floppy disk capacity wasn't magic. It wasn't random improvement. It was the result of careful engineering, of understanding the physics, of finding clever ways to encode information more densely, more efficiently, more reliably. Let's slow down and explore how this happened, how engineers doubled, then tripled, then quadrupled the amount of data that could fit on the same physical disk. The story begins with something called encoding, the method by which digital information, ones and zeros, gets translated into magnetic patterns on the disk surface. Those early 8-inch floppy disks used a method called FM encoding, frequency modulation, single density encoding. And while it worked, while it successfully stored data and retrieved it reliably, it was inefficient. Here's why. In FM encoding, every bit of data needed 2 magnetic transitions, 2 changes in magnetization. One transition served as a clock, a timing reference. The other transition represented the actual data, 1 or 0. Think about what this means. Half of your magnetic transitions, half of the patterns you're writing on the disk, aren't carrying information. They're just there for timing, to help the drive know where one bit ends and another begins. This was necessary in the early days. The electronics were simpler. The timing circuits were less sophisticated. You needed those explicit clock signals, those guaranteed transitions. But it meant you were using twice as much disk space as you theoretically needed. Engineers looked at this and thought, there must be a better way. And there was. It was called MFM, Modified Frequency Modulation, Double Density Encoding. MFM was clever, elegant in its simplicity. Instead of putting a clock transition before every data bit, MFM only inserted clock transitions when necessary. when there would otherwise be too long a gap between transitions, when the timing might become ambiguous. The rules were straightforward. When writing a 1, always write a transition. When writing a 0, only write a transition if the previous bit was also a 0. Otherwise, nothing. No transition, just the absence of change. This simple modification, this small change in the encoding rules, roughly doubled the capacity. The same disk, the same physical space, the same magnetic coding, but now holding twice as much data. MFM became the standard for later 8-inch disks and most 5¼ disks. It was efficient, reliable, and it worked with electronics that were still relatively simple and affordable. But encoding was only part of the story. There were other ways to increase capacity, other knobs to turn, other parameters to optimize. Track spacing. This was crucial. Imagine those concentric circles on the disk surface. Those tracks. In early disks, they were spaced relatively far apart, conservatively, with plenty of margin for error. But as manufacturing improved, as head positioning became more precise, engineers realized they could pack tracks closer together, tighten the spacing, fit more tracks on the same disk surface. This required better mechanical precision. The head positioning mechanism had to be more accurate, more repeatable. It had to reliably find track 57, even if track 57 was now narrower and closer to track 56. But it was doable. Manufacturing techniques improved, tolerances tightened, and track density increased. Data rate. This was another variable. The speed at which bits were written to and read from the disk, measured in kilohertz. The faster you could write bits, the more bits you could fit in a single track. High-density 8-inch and 5¼ drives typically ran at 360 revolutions per minute, a standard speed. Comfortable, reliable. And they used a 500 kilohertz bit clock for high-density formats. Lower capacity 5¼ disks often used a 250 kilohertz clock. Half the speed, half the bits per track. This was a deliberate choice. Slower speeds were more forgiving, required less sophisticated electronics, cost less to implement. But when you wanted more capacity, when you were willing to invest in better components, you could double that clock rate. Write bits twice as fast, pack twice as much data into each track. The progression from single density to double density wasn't about changing the physical media, not primarily. It was about changing how you encoded the data, about using MFM instead of FM, about packing information more efficiently into the same physical space. Later improvements, moving to high-density formats, involved multiple changes. Better coatings on the disk surface, finer magnetic particles that could be magnetized in smaller regions, tighter track spacing, higher data rates, all working together. And there were the magnetic coatings themselves, those layers of iron oxide. The quality and characteristics of these coatings improved over time. Early coatings were relatively coarse. The magnetic particles were larger. The layer was thicker. This worked fine for early densities. But as engineers tried to pack more data into smaller spaces, they needed better coatings, finer particles, more uniform distribution, thinner layers, better binding materials that held the particles in place without adding unnecessary thickness. Each improvement allowed for higher density, stronger signals, more reliable reading and writing. The transition from standard density to high density in 3.5-inch disks involved a different magnetic coating. High-density disks used cobalt-enhanced media, different magnetic properties, able to sustain higher coercivity, able to be magnetized more strongly, able to pack transitions closer together. This is why you couldn't just format a standard density disk as high density and expect it to work reliably. The media was different, not just in how it was formatted, but in its physical composition, its magnetic characteristics. High-density drives could often read standard density disks. The drive would detect the format, adjust its parameters, slow down its data rate, widen its tolerances, backward compatibility. But a standard density drive couldn't read high-density disks. The signals were too weak, the transitions too close together, the media too different. Engineers had to balance many factors: density versus reliability, speed versus cost, compatibility versus innovation. Every improvement in one area had to be weighed against potential compromises in others. And through it all, through decades of refinement, the fundamental architecture remained constant. The spinning disk, the moving head, the magnetic encoding. What changed was the precision, the sophistication, the efficiency. Consider what this meant in practical terms. That original 80 kilobyte 8-inch disk from 1971. By the early 1980s, roughly a decade later, 8-inch disks could hold 1.2 megabytes, 15 times more data. Same physical size, same basic mechanism. The 3.5-inch high-density disk at 1.44 megabytes. In a package dramatically smaller than that original 8-inch disk, with better durability, better reliability, higher density by almost any measure you could choose. This wasn't luck. This wasn't accident. This was engineering, systematic, methodical, building on previous work, learning from experience, pushing boundaries while maintaining reliability. But there were limits, physical limits that even clever engineering couldn't overcome indefinitely. The air bearing we discussed earlier, that microscopic gap between the head and the disk surface. As you tried to pack data more densely, as magnetic transitions got closer together, you needed the head to fly lower, closer to the media, to maintain signal strength, to read those tiny variations in magnetization. But you couldn't go too low. Get too close and you risked contact. Friction, damage. The head scraping against the surface, the coating wearing away, the delicate balance destroyed. Dust became more critical. A particle that was negligible at lower densities became a catastrophic obstacle at higher densities, like a boulder in the path of that flying head. Heat was a factor. As data rates increased, as electronics worked faster, managing heat became more important. Too much heat and magnetic properties changed. Signals degraded. Reliability suffered. Mechanical precision hit practical limits. You could only make positioning mechanisms so accurate, only hold tolerances so tight, only maintain alignment so precisely. Eventually, the cost of further improvement exceeded what the market would bear. And there was the fundamental limitation of the media itself. Magnetic particles can only be made so small. Magnetization can only be packed so densely. Below certain thresholds, thermal effects start to matter. Random fluctuations, quantum uncertainties. The bits themselves become unstable. Engineers in the late 1980s and early 1990s pushed close to these limits. The 2.88 megabyte extended density format represented near the practical maximum for floppy disk technology, double the standard capacity, but requiring more expensive drives, more sophisticated electronics, more stringent manufacturing tolerances, and ultimately, not worth it. Because by that point, other technologies were emerging. Hard drives were getting cheaper and larger. CD-ROMs were appearing. The cost-benefit calculation was shifting. But before we get to the decline, before we talk about what replaced the floppy disk, let's pause and appreciate what was accomplished. From FM to MFM encoding, from wide tracks to narrow tracks, from coarse magnetic particles to fine particles, from simple timing circuits to sophisticated data separation electronics. each improvement building on the last, each generation teaching lessons that informed the next. The engineers who worked on floppy disk technology weren't just solving immediate problems. They were developing techniques, learning principles, building knowledge that would apply to hard drives, to tape systems, to every form of magnetic storage that would come after. Error correction became more sophisticated. Methods for detecting and correcting bit errors improved. This knowledge transferred to other storage technologies. Servo systems for positioning heads became more precise. This precision enabled hard drives with thousands of tracks per inch, densities that would have seemed impossible in the floppy disk era. Understanding of magnetic materials deepened. The relationship between particle size and density, between coercivity and stability, between coating thickness and signal strength. All of this knowledge fed into the development of better storage media across all magnetic technologies. The floppy disk was a school, a proving ground, a place where engineers learned to push the boundaries of what magnetic storage could do. And those lessons, that accumulated knowledge, extended far beyond the floppy disk itself. But every technology has its limits. Every solution eventually meets problems it cannot solve. And as we approach the late 1990s and early 2000s, as file sizes grew larger and larger, the floppy disk's limitations became increasingly apparent. Not because the engineering was flawed, not because the technology didn't work, but simply because the world had changed. What we needed from storage had changed. And the floppy disk, elegant and reliable as it was, could only stretch so far. Every technology has its season, a time when it's exactly what the world needs, a time when it solves the right problems in the right way, and then, eventually, a time when the world moves on. The floppy disk served faithfully for nearly 3 decades, but nothing lasts forever, and by the late 1990s, the cracks were beginning to show. Not in the technology itself, but in the growing gap between what the floppy disk could offer and what people needed. Let's talk about fragility first, about the vulnerabilities that were always there, lurking beneath the surface, but became more and more problematic as data became more precious. Despite their protective jackets, despite their rigid plastic shells in the case of 3.5-inch disks, floppy disks were vulnerable. More vulnerable than they seemed, more vulnerable than people often realized, until it was too late. Dust, such a simple thing, particles in the air, invisible most of the time. We live with dust constantly. It settles on shelves, floats in sunbeams, accumulates in corners, harmless, ignorable. But to a floppy disk, dust was catastrophic. Remember that air bearing, that microscopic gap between the head and the magnetic surface, a gap measured in millionths of an inch. A particle of dust, even a small one, was enormous compared to that gap. If dust got onto the magnetic surface, if it settled there, the spinning disk would carry it around. Eventually it would pass under the read-write head, and then contact. The head would hit the particle, scrape against it, potentially damage the magnetic coating, create an error, a bad sector, lost data. The protective jacket helped. The sliding shutter on 3.5-inch disks helped. But they weren't perfect seals. Open a disk drive, insert a disk, eject it. Each time, an opportunity for dust to enter, to settle, to wait for the right moment to cause problems. Heat was another enemy. Magnetic media is sensitive to temperature. Too much heat and the magnetic properties change. The carefully aligned particles begin to lose their orientation. Data degrades, becomes unreliable, disappears. Leave a floppy disk in a hot car in summer, on a sunny dashboard, in direct sunlight. The temperature inside that car could easily reach levels that would damage the disk. Not necessarily immediately, not dramatically, but gradually, subtly, corrupting data in ways you might not notice until you tried to read it. Moisture, humidity, water. These were threats too. The magnetic coating could absorb moisture, swell slightly, change its properties. The adhesive binding the magnetic particles could weaken. The disk surface could become sticky, difficult for the drive to read. Spill coffee on a floppy disk and it was likely ruined. Drop one in a puddle. Disaster. Even storing disks in a damp basement could cause problems over time. Gradual degradation, slow corruption, and magnetic fields. This one was insidious because magnetic fields are invisible, unpredictable, everywhere. Place a floppy disk too close to a speaker. Speakers contain magnets, strong ones. The magnetic field from a speaker could partially erase or corrupt data on a nearby disk. Set your disk down on top of a CRT monitor. Same problem. The deflection coils in the monitor generated strong magnetic fields. Electric motors, transformers, anything with strong electromagnets or permanent magnets, all potential threats. You couldn't see the danger. You couldn't feel it. But it was there, waiting to scramble your carefully stored ones and zeros. Even the Earth's magnetic field could slowly affect disks stored for long periods, years, decades. The effect was gradual, but real. Archival storage of floppy disks was never as reliable as people hoped. Physical damage was perhaps the most obvious vulnerability. Despite the protective shell, despite the improvements in the 3.5-inch format, floppy disks could still be damaged. Bend a 5.25-inch disk too much and you might crease the media inside. Ruin it. Drop a 3.5-inch disk just right, or just wrong, and the internal components could shift. The magnetic disk could become misaligned with its protective shell. The metal shutter on 3.5-inch disks could be bent, jammed, broken off. The metal hub reinforcement could be damaged. Anything that affected the precise mechanical alignment between disk and drive could cause problems. And then there was simple wear. Every time a disk was used, every time it spun in a drive, every time the head passed over its surface, microscopic wear occurred. The magnetic coating would gradually thin. The head would gradually deteriorate. Error rates would slowly increase. Most disks could withstand hundreds or thousands of uses, but not infinite uses. Eventually, with enough read-write cycles, a floppy disk would fail. The question was never if, only when. All of these vulnerabilities were manageable when floppy disks were the best option available, when the alternative was punch cards or nothing, when storage capacity wasn't critical, when data could be backed up easily. But as computing matured, as data became more important, as people stored more critical information on computers, these vulnerabilities became less and less acceptable. And then there was the capacity problem, the limitation that ultimately doomed the floppy disk more than any physical fragility. 1.44 megabytes. That was the standard, the ceiling, the maximum that the ubiquitous 3.5-inch format could offer for most users. In the early 1990s, 1.44 megabytes was reasonable, not generous, but workable. A word processing document might be 50 kilobytes, a spreadsheet, 100 kilobytes. Small programs could fit on a single disk. Larger programs might need 2 or 3 disks. Annoying but manageable. But file sizes were growing, exponentially, relentlessly. Digital photos became common, even compressed. A single photo might be several hundred kilobytes, a megabyte or more. Suddenly, one floppy disk couldn't even hold a handful of photos from your digital camera. Software grew larger. Operating systems became more complex. Applications added features, graphics, multimedia. Windows 95 came on 13 floppy disks, 13. Installing it meant sitting at your computer for what felt like hours. Swapping disks, one after another, after another. Insert disk 2. Wait. Insert disk 3. Wait. Insert disk 4. And heaven help you if one of those 13 disks was damaged, if one had a bad sector, if one couldn't be read. The entire installation would fail, and you'd have to start over. Music files. MP3s emerged in the late 1990s. A single song, compressed, was 3 to 5 megabytes, too large for a floppy disk. Impossible to carry your music on floppies. Video was completely out of the question. Even highly compressed video clips were tens or hundreds of megabytes. The floppy disk couldn't come close. Hard disk drives were solving the capacity problem. They had been growing larger and cheaper for years. By the late 1990s, a typical computer might have a 2 or 3 gigabyte hard drive, thousands of times more storage than a floppy disk. But hard drives weren't removable. They lived inside your computer. They weren't portable. You couldn't take your hard drive to a friend's house to share files. You couldn't mail a hard drive across the country. For a while, there was a gap, a need for portable storage with more capacity than floppy disks, but more convenience than hard drives. Various companies tried to fill this gap. Zip disks were perhaps the most successful of these attempts. Created by Iomega, they looked like thick floppy disks, but they held 100 megabytes. Later versions held 250 megabytes, even 750 megabytes. Zip disks were faster than floppies, more reliable, much higher capacity. For a few years in the mid to late 1990s, zip drives were popular. Many computers came with zip drives installed or available as options. But zip disks had problems. The drives were expensive. The disks themselves were expensive compared to floppies. And there were reliability issues. The infamous click of death. A mechanical failure that would destroy not just the disk currently in the drive, but potentially the drive itself. Other formats tried. SuperDisk, Jazz drives, LS120. Each offered higher capacity. Each tried to maintain some compatibility with standard floppies. Each found some market, but none became universal. And then, in the late 1990s, a technology appeared that would change everything. That would finally, truly, completely replace the floppy disk. The CD-ROM compact disc had existed for music since the early 1980s. But CD-ROM drives that could read data disks in computers, became standard in the mid-1990s. And they offered something revolutionary. 650 megabytes, later 700 megabytes, on a single disk. Over 400 times the capacity of a floppy disk. And the disks were cheap, mass-produced, reliable, immune to magnetic fields, relatively durable. Software distribution moved to CD-ROM almost overnight. Instead of a stack of 13 floppy disks, Windows came on a single CD. Office software, games, everything fit on one disk, maybe two for very large applications. CDR technology emerged, recordable CDs. For a modest investment, you could burn your own CDs, back up data, share files, create your own distribution media. The capacity was enormous compared to floppies. The cost per megabyte was far lower. DVD-S followed, even higher capacity, 4.7 gigabytes, enough for entire movies, entire application suites, more data than most people generated in months. But CDS and DVD-S had a weakness. You couldn't easily update them, couldn't rewrite them. CDRW existed, rewritable CDS, but they were slower, more expensive, less reliable, not ideal for day-to-day file transfer. And then, in the early 2000s, the final blow arrived. The technology that would truly end the floppy disk era. USB flash drives. Small, solid state, no moving parts. Plugged directly into a USB port, no drive required, no disks to swap. Just a small device, often on a keychain, that could hold initially dozens, then hundreds, then thousands of megabytes. Flash drives were everything floppy disks weren't. Durable. No magnetic fields to worry about. Drop them. Usually fine. Get them wet. Dry them out. Usually fine. No delicate mechanisms, no spinning platters, no flying heads. Fast. Much faster than floppy drives. Data transfer speeds that made floppies look glacial by comparison. Rewritable. Use them again and again. Millions of write cycles. Far more than any floppy disk could withstand. And capacities grew explosively. 32 megabytes, 64, 128, 256, 512, a gigabyte, 2 gigabytes, 4, 8, 16. Within a few years, a thumb-sized flash drive held more data than thousands of floppy disks. The price fell rapidly. By the mid-2000s, you could buy a flash drive with more capacity than a box of floppies for less money than that box of floppies would cost. Computer manufacturers responded to market reality. Floppy drives began disappearing from new computers, first as optional equipment, then not available at all. Why include a drive that most users would never need? That took up space? That added cost? By the early 2000s, the floppy disk had effectively disappeared from mainstream consumer use. A few holdouts remained. Some businesses kept using floppies for specific purposes. Some individuals kept boxes of old disks with archived data. But for practical purposes, for day-to-day computing, for file transfer and backup, and software distribution, the floppy disk was done. Obsolete. Replaced. Not because it stopped working, not because the engineering failed, but because the world had moved on. Because what we needed from storage had fundamentally changed. Because better alternatives existed. The floppy disk had served its purpose, had carried computing through a critical era, had enabled the personal computer revolution, had made portable data possible for millions of people. And now, its time had passed. Quietly, inevitably, the way all technologies eventually fade when their moment ends. The floppy disk may have disappeared from mainstream computing, from store shelves, from new computers, but it didn't vanish completely. Not entirely, not everywhere. In quiet corners of the world, in unexpected places, floppy disks still exist, still function, still serve their original purpose, sometimes by necessity, sometimes by choice, sometimes simply because replacing them would cost more than the benefit would justify. These aren't just museum pieces, not just relics preserved for nostalgia. These are working systems, critical systems, systems where the floppy disk remains, improbably, the best solution. Or at least, the solution that's still in place. Let's explore these hidden pockets where floppy disk technology lives on. High above the earth, in the cockpits of aircraft, floppy disks still fly. Not in new planes, not in the latest Boeing or Airbus models with their glass cockpits and digital everything, but in older aircraft, planes built in the 1980s and 1990s, still flying, still airworthy, still perfectly functional. Many of these aircraft use floppy disks to load navigation databases, avionics updates, flight management system data, the airports, the waypoints, the radio frequencies, all stored on floppy disks, loaded into the aircraft's computers through floppy drives that have been there since the plane was built. Why haven't these been upgraded? Why not replace the floppy drives with something modern? Because aviation moves slowly, deliberately. Every change to an aircraft system requires certification, testing, documentation. proof that the new system is at least as safe as the old system. This process is expensive, time-consuming, rigorous, and the floppy disk system works. It's proven, reliable, certified. Airlines know how to use it. Technicians know how to maintain it. The procedures are established. The training is in place. Replacing the floppy drives would require recertifying the avionics systems, updating manuals, retraining crews, installing new hardware throughout the fleet. The cost would be enormous. And for what benefit? The navigation data fits on a floppy disk. The update frequency is low. Once a month, sometimes less. So the floppy drives remain. And every month, somewhere in the world, a technician inserts a 3.5-inch floppy disk into an aircraft navigation computer. The disk spins, data transfers, the aircraft's database updates, and the floppy disk is removed, stored, ready for next month's update. It's practical, it works. And in aviation, where safety and proven reliability matter more than having the latest technology, that's enough. On factory floors, in industrial facilities, legacy machinery tells a similar story. Manufacturing equipment built in the 1980s and 1990s often uses floppy disks for storing configuration data, machine parameters, CNC programs, operational settings. These are specialized machines, expensive machines, built to last decades. A CNC mill from 1985 might still be producing parts today, still accurate, still capable, still economically viable, and it still has a floppy drive for loading machining programs. The manufacturer might be out of business. The original programmers might be retired. But the machine works. It produces good parts. It makes money. Why replace it? And so the floppy disks remain, carefully preserved, backed up, often onto modern media, but still maintained in floppy format, because that's what the machine needs. The machine doesn't know about USB drives, doesn't have Ethernet, doesn't understand SD cards. It understands floppy disks. And as long as the machine keeps working, as long as parts keep being produced, the floppy disks will continue to serve. In medical facilities, similar stories unfold. Older medical imaging equipment, diagnostic machines, laboratory analyzers, built when floppy disks were standard, still functional, still accurate, still doing their jobs. These machines are expensive. Medical equipment requires FDA approval. Replacing them isn't just a matter of buying new hardware. It's navigating regulatory approval, training staff, validating that the new equipment performs at least as well as the old. Many healthcare facilities make a calculation. If the equipment still works, if it still provides accurate results, if it's still safe, then keep using it, even if it means maintaining a supply of floppy disks, even if it means keeping old computers around that can still read those disks. The military, unsurprisingly, also maintains systems that use floppy disks, not in frontline systems, not in cutting-edge technology, but in legacy systems, infrastructure, equipment that was built to last, that was over-engineered for durability and longevity. Communication systems, logistics systems, training equipment. Some of these systems are decades old, but they're robust, hardened, proven, and replacing them would cost millions or billions for functionality that already works. So the floppy disks persist in secure facilities, in carefully controlled environments, backed up, maintained, still serving their purpose. In research laboratories, floppy disks sometimes survive for different reasons. Not because the equipment is impossible to replace, but because the cost-benefit doesn't justify replacement. A piece of test equipment, a specialized instrument, it works, it's calibrated, it produces reliable data, it has a floppy drive for data export. Sure, you could replace it with something newer, But the new equipment costs $50,000. The old equipment still works fine. It just needs floppy disks. So the lab keeps a small supply, maybe a box of 20 disks, enough to last years. The graduate students learn to use them. It becomes part of the lab culture. Oh yeah, that machine uses floppies. There's a box in the drawer. Make sure you return them when you're done. These scenarios, aircraft, factories, hospitals, military, research labs, these aren't rare exceptions. They're more common than you might think, scattered around the world, hidden in plain sight. Ordinary people working with decades-old storage technology because it's still the right tool for the job. But there's another category of floppy disk users, people who choose to use them, not because they have to, but because they want to. Retro computing enthusiasts, people who love old computers, classic machines from the 1980s and 1990s, Commodore 64s, Apple IIs, IBM PCs, Atari STs, Amiga computers. These machines were designed around floppy disks. That's how they loaded software, how they saved data. And if you want to use these machines as they were meant to be used, if you want the authentic experience, you need floppy disks. The retro computing community maintains supplies of floppy disks, tests them, preserves them, shares them. There are online forums dedicated to finding working drives, repairing broken mechanisms, creating new disks from old stock. Some enthusiasts have found ways to simulate floppy drives with modern hardware, devices that plug into the floppy drive port but actually read data from SD cards or USB drives. The computer thinks it's using a floppy, but the data comes from modern storage. These solutions work. They're practical. But some purists prefer the real thing, the authentic sound of the drive seeking, the ritual of inserting a physical disk, the tangible connection to computing history. Musicians and artists form another community of intentional floppy disk users, vintage samplers and synthesizers from the 1980s and 1990s. Many of them use floppy disks to store sounds, patches, sequences. These instruments have unique characteristics, unique sounds. They're prized by producers and musicians who appreciate their specific sonic qualities. And many of them still work, still create music, still have their original floppy drives. If you're a musician using an EMU sampler from 1988, if that particular machine has the sound you need, then you're going to need floppy disks. Not because you can't find alternatives, but because that's part of the workflow, part of the instrument. There's even a small market for new old stock floppy disks. Boxes of disks that were manufactured 20 or 30 years ago, never opened, sealed in their original packaging, stored in warehouses, now sold to enthusiasts and niche users who still need them. The prices can be surprisingly high, not because the disks themselves are valuable, but because supply is limited and fixed. No one is manufacturing new floppy disks. No one is building new drives. What exists now is all that will ever exist. And so we have this strange situation, a technology that's completely obsolete for mainstream use, that hasn't been included in consumer computers for over a decade, that most young people have never seen or used, but which persists in pockets, in niches, in places where it still makes sense, or where the cost of change outweighs the benefit, or where people choose to keep it alive for passion, for art, for preservation. This is the nature of technology. Complete obsolescence is rare. Technologies don't vanish overnight. They fade, gradually, unevenly, disappearing from most places while lingering in others. 50 years from now, will there still be floppy disks in use somewhere? Possibly, probably, in some specialized system, some preserved aircraft, some museum that keeps its old computers running, some artist who treasures that particular piece of vintage equipment. The floppy disk mainstream era ended 2 decades ago. But its absolute end? That might be decades more in the future, or might never quite arrive. Technologies sometimes refuse to die completely. They find corners, crevices, places to persist long after everyone thought they were gone. And there's something beautiful about that. Something that speaks to human creativity and persistence. We don't just abandon things because they're old. We find ways to keep them working, to maintain them, to preserve them, to value them for what they still offer. The floppy disk in an old CNC mill isn't there because anyone loves floppy disks. It's there because the mill still makes good parts. The technology serves a purpose, and as long as it does, as long as it works, why change it? The floppy disk in a musician's sampler isn't there because it's the best storage technology. It's there because that's how the instrument works. And the musician values the instrument, values its sound, values its character. The floppy disk in the aircraft navigation system isn't there because airlines are nostalgic. It's there because it's certified, proven, safe. And in aviation, those qualities matter more than being modern. These aren't failures to update. They're pragmatic decisions, cost-benefit analyses, recognition that new isn't always better, that sometimes the old way still works fine. And in a world that often seems obsessed with the newest, the latest, the most advanced, there's something quietly satisfying about these pockets of persistence, these places where the floppy disk, that elegant solution from the 1970s, continues to spin, to store data, to serve. Not everywhere, not for everyone, not even for most people, but somewhere, for someone, still working, still useful, still alive. Before we close this journey, before we let sleep fully take hold, let's consider one more thing. One final perspective on the floppy disk and what it meant. What it still means. Because the floppy disk didn't just exist and then vanish. It left something behind. Something more than the devices still humming away in aircraft and factories. Something more than the memories of those who use them. It left ideas, concepts, ways of thinking about data, ways of organizing information, principles that carried forward into everything that came after. The floppy disk's greatest legacy isn't the technology itself. It's how it changed what we expected from computers, how it shaped the evolution of storage, how it taught us, engineers and users alike, what portable data could mean. Let's start with something you see every day, something so common you probably don't think about it anymore. The save icon. Open almost any application, word processor, spreadsheet, image editor, email program. Look for the save button. There it is. That familiar shape. A square with a slightly angled top. A small rectangular detail in the upper portion. Sometimes rendered simply. Sometimes with slight variations. It's a floppy disk. Specifically, a 3.5-inch floppy disk. Viewed straight on, stylized, simplified, but unmistakable if you know what you're looking at. This icon became universal in the 1980s and 1990s, when floppy disks were how people saved their work. When save your file literally meant write it to a floppy disk. The icon made perfect sense. It was direct, literal. Save meant floppy disk. But here's what's remarkable. The icon persists, decades after floppy disks disappeared from computers, decades after most people stopped using them. Even now, in an era where many young computer users have never seen a physical floppy disk, never used one, possibly don't even know what one is, the save icon remains. Designers keep it because it works, because users recognize it instantly, because the association between that shape and the concept of saving is so deeply embedded in computing culture that changing it would be more confusing than keeping it. The floppy disk, as a physical object, is obsolete. But as a symbol, as an icon, it's eternal. It has transcended its original purpose, become pure meaning, pure concept, divorced from the physical reality it once represented. This is a kind of immortality, not the immortality of continued use, but the immortality of a language, of symbols. The floppy disk lives on as an idea, as a universal shorthand for preservation, for keeping, for making permanent. But the influence goes deeper than icons. The floppy disk established patterns, expectations, ways of thinking about storage that we still carry with us. The idea of removable media. Before floppy disks, computer storage was mostly fixed. Magnetic tape had to be mounted on large reel-to-reel systems. Disk packs for mainframes were removable, but huge and expensive. Punch cards were removable, but barely storage in the modern sense. The floppy disk normalized the concept of storage you could hold, storage you could own personally, storage you could take with you. Pop it out of one computer, walk to another computer, insert it. Your data traveled with you. This seems obvious now, but it wasn't always. It had to be invented, popularized, accepted. The floppy disk did that. It made removable personal storage a standard feature of computing. Every USB drive you've ever used, every SD card, every external hard drive stands on the foundation the floppy disk built. The expectation that you can carry your data, that storage is portable, that your files can move between machines. The floppy disk taught us to expect this. File systems, the way data is organized on storage media, the concepts of tracks and sectors, directories and subdirectories, file allocation tables. All of these were refined and standardized during the floppy disk era. These organizational principles didn't originate with floppy disks. They have roots in earlier storage systems. But the floppy disk was where they were perfected, where they were made accessible, where millions of people encountered them for the first time. And these principles carried forward. Hard drives use tracks and sectors. SSDs, despite having completely different physical mechanisms, still present data in logical sectors. The abstractions developed for floppy disk proved so useful, so flexible, so well designed, that they remained relevant even as the underlying technology changed completely. Error correction. Floppy disks weren't perfectly reliable. Magnetic media never is. So engineers developed methods to detect errors, to correct them when possible, to fail gracefully when correction wasn't possible. These techniques matured during the floppy disk era. Cyclic redundancy checks, Reed-Solomon codes, sophisticated algorithms that could detect corrupt data and sometimes reconstruct it from the remaining good data. These methods didn't stop with floppy disks. They evolved, improved, but the foundation was laid. The problems were identified. The solutions were developed. And every modern storage system, every hard drive, every SSD, every cloud storage service, uses descendants of these error correction techniques. The concept of formatting, the idea that storage media needs to be prepared before use, organized into tracks and sectors, initialized with file system structures. This became common knowledge during the floppy disk era. You couldn't just use a floppy disk straight out of the box, you had to format it first. Choose a file system, allocate space for directory structures. This was a user-visible process, something people learned to do, expected to do. And this understanding carried forward. Even though modern storage often comes pre-formatted, even though the process is increasingly hidden from users, the concept remains. Storage has structure. That structure must be created. Users with technical knowledge understand this because the floppy disk taught it. Standardization itself. The floppy disk helped establish the principle that storage formats should be standardized, that a disk formatted on one computer should be readable on another, that interoperability matters. This wasn't always the case. In the early days of personal computing, different manufacturers used different formats, incompatible systems, data that couldn't be shared. But market forces pushed towards standardization. And the floppy disk, particularly the 3.5-inch format, became a true standard, universal, cross-platform. A disk formatted on a PC could be read by a Mac, and vice versa. This expectation of compatibility, of standardization, of data portability across different systems, this became a baseline assumption, something users expected, something manufacturers had to provide. The floppy disk established this norm. Engineers learned lessons too, technical lessons that informed the development of later storage technologies. The importance of data density, the relationship between signal strength and flying height, the trade-offs between capacity and reliability, the challenges of mechanical precision, the physics of magnetic recording. All of these lessons were learned, often the hard way, during decades of floppy disk development, and they applied directly to hard drive development, to tape systems, to any magnetic storage technology. Hard drives use similar principles to floppy disks, spinning platters, flying heads, magnetic recording, but pushed to extremes, much higher speeds, much tighter tolerances, much higher densities, the engineering that made modern hard drives possible. Much of it came from lessons learned with floppy disks. Even solid-state drives, which use completely different physics, benefited from conceptual frameworks developed during the magnetic storage era. Ideas about sectors, about wear leveling, about managing limited write cycles. The problems were different, but the thinking, the approaches to solving problems, had roots in earlier technologies. The floppy disk also taught us about obsolescence, about technology life cycles, about the inevitable progression from cutting-edge to commonplace to obsolete. The 8-inch disk seemed revolutionary in 1971. By 1985, it was rare. By 1990, nearly extinct. 15 years from revolution to obsolescence. The 5.25-inch disk dominated the early PC era, but by the mid-1990s, it was fading. By 2000, gone from most machines. Even the 3.5-inch disk, the format that seemed like it might last forever, the one that became the universal standard, had a limited run, common from the mid-1980s to the mid-2000s. 20 years at the peak, then decline, then disappearance. This pattern of technological rise and fall, this life cycle, played out visibly with floppy disks. An entire generation of computer users watched it happen, experienced it directly, saw one format replace another, saw capacity increase and then become insufficient, saw the whole technology eventually become obsolete. This experience taught an important lesson. Technology moves. Nothing stays current forever. What seems permanent today will be replaced tomorrow. Adapt. Expect change. Don't become too attached to any specific technology. This lesson has served us well. In an industry where change is constant, where new technologies emerge continuously, where yesterday's standard is tomorrow's legacy system, the floppy disk, by going through its complete life cycle so visibly, helped prepare us for this reality. And there's one more legacy, perhaps the most important. The floppy disk helped democratize computing, made it personal, made it accessible, made it something ordinary people could use. Before floppy disks, computing was institutional. Mainframes in controlled rooms, specialists operating expensive equipment, data that lived in the machine or on unwieldy media. The floppy disk made data portable, personal, yours. You could carry your files in your pocket, take them to a friend's house, mail them across the country, share them, back them up, control them. This shift from computing as an institutional activity to computing as a personal tool. The floppy disk was crucial to this transition. It gave people ownership of their data, made them independent, put control in their hands. And once people had that control, once they experienced the freedom of portable personal data, they never wanted to give it up. Every subsequent storage technology had to provide this, had to enable personal data ownership. The floppy disk established this expectation, made it non-negotiable. So yes, the floppy disk is obsolete. The technology itself has been superseded, replaced by better options, faster, larger, more reliable, more convenient. But its influence, that remains. In every USB drive, every cloud storage account, every save button, every concept of removable media, every expectation of data portability, every standard for interoperability. The floppy disk doesn't need to exist anymore as hardware. It exists as ideas, as expectations, as principles, as foundations that everything else builds on. This is the truest form of legacy, not continued use, but influence that permeates everything that comes after. Ideas so fundamental they become invisible. Assumptions so basic they're rarely questioned. The floppy disk taught us what storage could be, should be, must be. And in doing so, it shaped the entire trajectory of computing, not just in the decades when it was actively used, but in all the decades since, and likely in all the decades to come. Technologies will continue to evolve. Storage will become faster, larger, more reliable, more convenient. We'll see innovations we can't currently imagine, capabilities that would seem like science fiction today. But underneath those innovations, underneath those advances, will be ideas and principles that trace back, in one way or another, to that spinning magnetic disk in a protective jacket, to that elegant solution from the 1970s, to that bridge between punched cards and modern storage. The silent logic of the floppy disk, still there, still present, still influencing, even now, even in a world where the floppy disk itself has faded into history. It solved problems, enabled possibilities, changed expectations, taught lessons, and in doing so, became part of the foundation of modern computing, invisible now, but essential, eternal. And with that, as our journey through floppy disk history comes to a close, as sleep approaches, we can rest knowing that some technologies never truly die. They transform. They persist as ideas, as influences, as the silent logic underlying everything that comes after. The floppy disk is gone, but the floppy disk remains, in symbol, in concept, in principle, in the very structure of how we think about data. Silent, elegant, eternal. Good night.